Hey there and welcome. If you've ever just stared at a physics problem and felt your brain totally freeze up, you are definitely in the right place. In this explainer, we're going to break down a really powerful, step-by-step strategy that can turn all that confusion into real confidence. So let's get right into it. You know the feeling, right? We've all been there. You're looking at some problem with a block on an incline or a rocket taking off, and there are just a dozen different numbers and variables flying around. It is so easy to feel completely overwhelmed and not even have a clue where to begin. But what if I told you there's a blueprint? A clear path you can follow every single time. Look, the real key here isn't about memorizing a bunch of different solutions for a bunch of different problems. It's about learning a reliable system. We're going to build a 4-step framework based on proven strategies that you can use to tackle pretty much any problem that involves forces. So here's our roadmap. First, we're going to sketch the situation just to get a picture of what's happening. Second, we'll get everything organized by identifying our system and listing out all our variables, what we know and what we don't. Third, we apply the big one, Newton's second law. And finally, and this is an absolutely crucial last step, we'll check if our answer actually makes sense in the real world. Okay, but before we can even use that blueprint, we need to master a really critical concept that honestly trips up so many students. And that's the difference between internal and external forces. Getting this right is the key to setting up every single problem correctly. So here's the most important point. We have to define our system of interest. Just think of it like drawing a big bubble around the thing or things we want to analyze. And why does this matter so much? Well, it's because Newton's second law, good old F equals ma, only cares about the external forces, the forces that actually cross the boundary of that bubble from the outside. This slide gives us a perfect example to wrap our heads around this. Let's imagine our system is Tarzan. The tension from the vine pulling up on him, that's an external force. It's coming from outside and crossing the boundary of our Tarzan bubble. But what about the force of his biceps contracting? Well, that's internal. His own arm is pulling on his own body. That force can't change his overall motion through the air. Only external forces can do that. All right, let's do a quick check to see if you're with me on this. If we define our system as the entire car, is the force that the engine creates internal or external? I'll give you a second. You got it? It's internal. The engine is pushing on other parts of the car. It's all inside the bubble. The external force that actually makes the car accelerate forward is the force of the road pushing on the tires. It's a super common mistake to make, but that distinction is crucial. Okay, now that we've got that critical concept locked in, it's time to get our hands dirty and actually apply our 4-step blueprint to a real problem. Let's start with a classic physics example, a rocket launch. So here's the problem statement, straight from the textbook. We've got the rocket's mass, we know the upward thrust from its engines, and we know the downward force of air resistance. Our one and only goal here is to figure out its acceleration. Let's start with steps 1 and 2. First, we just sketch the rocket, and then we define it as our system of interest. Now, for the important part, we draw the free body diagram. So what external forces are acting on it? Well, we've got the thrust, which we'll call T, pushing up. We've got air resistance, F, pushing down. And of course, you can't forget the rocket's own weight, W, also pulling it down. And now for step 3. This is where we bring in the big gun of physics here, Newton's second law. It just states that the total or net force on an object is equal to its mass times its acceleration. As you can see, this simple, powerful equation, F net equals m times a, is the key to unlocking the whole problem. So what we do now is basically turn that picture, our free body diagram, into a mathematical equation. We'll decide that the up direction is positive. That means our net force is the upward thrust minus the downward air resistance and also minus the downward weight. Our diagram leads us directly to the equation you see right here, T minus F minus mg all equals ma. Now for the easy part. We just do a little algebra to solve for A, plug in all the numbers from the problem statement, and after we run the calculation, we get our final answer. The rocket's acceleration is 6.20 meters per second squared. And finally, our crucial step 4, the sanity check. Does this number even make sense? Well, let's think about it. The upward force is about 12.5 million newtons. The total downward force, when you add up air resistance and weight, is about 9.4 million newtons. Since the upward force is obviously a lot bigger, we should absolutely expect a positive upward acceleration. So, yep, the answer is reasonable. See, the process works. It takes a complicated problem and makes it manageable. So let's run through it just one more time with a different kind of problem to really make sure this method sticks. This time, we'll take a look at the forces involved in a high jump. Okay, here's the setup. We have a 70-kilogram athlete, and we know that somehow they achieve an incredible upward acceleration of 4 times g. That's 4 times the acceleration of gravity. The question is, just how much force do they have to exert on the ground to make that happen? All right, let's apply our strategy. Steps 1 and 2. Our system of interest is the high jumper. At that exact moment they push off, what external forces are acting on them? Well, there's the jumper's weight, W, pulling them down, and then there's that big upward force, F, that the ground exerts back on them. And that's it, see? Nice and simple. Now for step 3. Let's bring in Newton's second law again. F net equals ma. The net force is just the upward force F minus the downward weight W. So F minus W equals ma. Now here's the cool part. The problem tells us that A is equal to 4g. If we substitute that in and rearrange the equation to solve for F, we find something really elegant. The force required is exactly 5 times the jumper's own weight. And when we go ahead and plug in the numbers, that's 5 times 70 kilograms times 9.8 meters per second squared, we get our final answer, 3,430 newtons. Okay, let's do our final check. Is this a reasonable number? I mean, think about it. Just to stand still, the ground has to push up with a force equal to their weight. To accelerate upwards at all, the force has to be bigger than their weight. So to accelerate upwards at 4 times the force of gravity, a force that's 5 times their body weight sounds extreme, right? But for an explosive, powerful athletic movement, it's absolutely in the realm of possibility. The answer makes perfect sense. So there you have it. In just a few minutes, we've gone from staring at a blank page, feeling stuck, to systematically breaking down and solving 2 very different physics problems. That feeling of being stuck gets replaced by the confidence of actually having a plan. This right here is your takeaway. This is the toolkit you can now apply to the next problem you face and the one after that. Just remember the steps. Sketch it out, define your system, and identify all the external forces. Apply Newton's second law. And always check to see if your answer is reasonable. And that brings us to one last thought. You know, this method of breaking down a huge, complex challenge into a logical sequence of manageable steps, that isn't just for physics. How could you use this same blueprint, visualize, organize, apply a core principle, and check your work to tackle other complex problems in your own life? It's something to think about. I really hope this was helpful, and thanks